This is our first video on heat, and in this video we will talk about the difference between heat and temperature, the thermal expansion for linear area and the volume expansion when the temperature changes, and we also will talk about the ideal gas equation and the law. So I think this is what I can fit in this video. So let's look at maybe even kinetic theory of gas and assumptions. So we will see if we can get this far. So let's look at some questions related to this new topic, so you understand how to use formulas and how to apply the knowledge that we will be covering. I will start with the picture that I have in front of you right now. And in this picture, I just took a snapshot from the temperature scales that's used in the world, and we use Fahrenheit in the United States, but like 99% of the world uses Celsius, but in science they use Kelvin. And if you see, they have the sign for degrees for Celsius, and they have the sign for degrees for Fahrenheit, but they don't use the sign of degrees for Kelvin. They only write Kelvin, no degrees Kelvin. So the absolute zero is going to be the 0 Kelvin. Nothing can pass below absolute zero. So absolute zero is 0 Kelvin, and it is impossible to reach because if an object has a mass, it has particles, and if the object has a mass, it has a volume. So if an object has a volume, that means it has pressure, but 0 Kelvin means all the particles stop moving. So there's no motion, and if there's no motion, you wouldn't be able to have a volume. This is probably one of the most simple explanations, but nothing can be below 0. And Kelvin and Celsius are good to use because the difference between them is 1 degree. So let's say if Kelvin goes... they have the same change. I shouldn't say 1 degree change, but if change of the temperature in Kelvin is 1 Kelvin, then the change of the temperature in Celsius also going to be 1 Celsius. So the change of the temperature in Celsius is still 1 degree Celsius. So if now you have 1 Kelvin, like if this was the scale and it said 1 Kelvin, then at this same level, you would have, instead of negative 273.15, you would have negative 272.15 degrees Celsius. You would add 1 degree higher for each gradient that you're moving up. So if Celsius moved up by 10, Kelvin moves up by 10. So 0 Kelvin is the same as negative 273 degrees Celsius. Fahrenheit, it's up to you if you want to remember. It's hardly ever used anywhere. There are formulas where you can convert. If you want to memorize the formulas, it's again up to you if you want to memorize the formulas. I haven't seen an AP exam ever given anything in Fahrenheit. It's usually Celsius and Kelvin. And you don't have to convert from Celsius to Kelvin and back if you see delta T. So let's say you had the temperature went from 0 Kelvin to 10 Kelvin, then delta T is equal to 10. And for Celsius, it would go from negative 273 degrees Celsius to negative 263 degrees Celsius. So the same delta T is 10 for both of them. So if you see delta T, it doesn't matter. You don't have to convert into Kelvin or Celsius. You just subtract two values that they give you. But if you see just T in the formula, that means you have to use it in Kelvin. So if you ever have in the formula T for the temperature, you have to use it in Kelvin. You cannot leave it in Celsius. And the difference between Kelvin and Celsius is 273 degrees. So 0 Kelvin is negative 270 degrees Celsius, and 0 Celsius is 273 degrees Kelvin. So thermal physics is a study of temperature, heat, and how they affect matter. Two objects are said to be in thermal contact if energy can be exchanged between them, and two objects are in thermal equilibrium if they are in thermal contact and there is no net exchange of energy. So if energy cannot flow, then they are in equilibrium. Thermal energy is the heat. So if temperature is the average kinetic energy of the molecules in the substance. So that is what temperature is. So I usually tell the students, when you go golfing and the ball is flying toward you, somebody will scream 4, so you have to watch it and move away so the ball does not hit you, because if the ball hits you, it hurts a lot. So imagine if you have millions of those balls hitting you at the same time. And that is exactly what's happening to your finger when you touch something hot and you burn your skin, because there are millions of molecules moving at the high speed. And when you touch this hot substance, it has high temperature. That means molecules move inside very fast. And then when your molecules come in contact with the molecules of the hot object, that energy from the hot object is transferred to you. So all energy always flows from hot to cold, and so the energy is transferred into your finger, and your finger cannot handle so many golf balls bombarding your finger. So this is where you get the burn. So heat is energy measured in joules, and temperature is Kelvin, Celsius, or Fahrenheit, and we're going to be using only Celsius and Kelvin. And also temperature has a definition. It is a measure of average kinetic energy of the particles in a substance, which is related to how hot or cold that substance is. It can be measured in Kelvin, Celsius, or Fahrenheit. And in standardized units, in all the problems you're going to be solving, you want to convert it in Kelvin, unless it is delta T, and you just can avoid doing that. So again, 0 degrees Kelvin is absolute zero. Nothing can be below that. 273 degrees Kelvin is the freezing point of water. So at 273 degrees Kelvin, it's the same as 0 Celsius. Good to remember. So 0 Celsius and 273 degrees Kelvin is the same thing when the water is freezing. And if you take notes, that would be good to write, because we're going to use this a lot. And then again, 0 Celsius, the same as 273 degrees Kelvin. And then boiling point of water is 100 degrees Celsius, which is easy to remember again. So 0 is freezing point, 100 degrees Celsius is boiling point, and it's the same as 373 degrees Kelvin, the boiling point of water. So you can see that I wrote it right here, and it's in our notes online as well, in our lessons. So the difference between Celsius and Kelvin is 273 degrees. And then the Fahrenheit has its own formula, and you can see it right here. You can convert one into another. Have never seen this related in AP exam, where you have to convert one Fahrenheit to Celsius or Kelvin. In this example, and I'm gonna skip it, you can do this yourself. They give you the temperature in Fahrenheit. They give you the temperature in Fahrenheit, and that's the change of the temperature. You can pause and read the question, and then they say convert these temperatures into Celsius and find the difference, and convert these temperatures into Kelvin and then find the difference. So you would use these formulas to find the Celsius, and then if you know Celsius, then you use this formula to convert to Kelvin. So I'm just going to give you an answer, and you can try this. So you have 22 degrees Celsius and 29 degrees Celsius. So the difference is going to be 7 degrees Celsius. And for the next one, for Kelvin, you would get 285 degrees, or Kelvin, I should not say degrees, and 292 Kelvin. And again, the difference between them is 7. So the difference in temperature is 7 degrees Celsius, or it is 7 Kelvin. And you see, it doesn't matter whether you converted one into another. You're just not allowed to use to leave them in Fahrenheit, because you have to convert them. thermal expansion. So thermal expansion is when the substance increases its length or volume or area based on the change of the temperature. So here in this equation, in the picture, you see how the bar got heated and its length has delta L change, and you can calculate this delta L by multiplying the initial length of the bar times its coefficient of linear expansion, and for every material it is different. So coefficient of linear expansion is a table for every material, and delta T by how much the temperature of this bar has changed. Here's another example where you can see that the expansion with the temperature. So in this case, you see the volume expansion, and the volume expansion has different formula, and so does the area expansion. So let's look at the formulas so we understand how to use them. So here are three different formulas, and they say if an object has an initial length L sub 0 along some direction at some temperature T sub 0, then the length increases by delta L for the change in temperature delta T. So for small changes in temperature, you can use delta L as it is given by the formula. So delta L is equal to alpha, and then so this sign is, so you have delta L is equal to, the sign is alpha, and then you have initial length and then the change of the temperature. And then and alpha is coefficient of linear expansion. If you want to calculate the volume exchange and the area exchange, you have to change the formula a little bit. So for delta area, for change in the area when the temperature changes, you have gamma, and then you have initial area and change of the temperature of that material. And gamma is the coefficient of area expansion, and if gamma is not given, you could take gamma and 2 times alpha. So if only alpha is given, if only linear expansion is given, you can replace gamma with 2 times alpha. And then for the change in volume with the temperature of most substances is proportional to the initial volume and the temperature change. So if you're looking for the change of the volume, again, you take beta, and beta is the coefficient of volume expansion. If beta is not given, you can say beta is equal to 3 times the linear expansion. So if that is not given in the problem, but you have linear expansion, you 3 times that number, and then times the initial volume and the change of the temperature. So this is the formulas, and let's look at how we use them. So in this question, they say that steel, and they give you the coefficient of linear expansion. Railroad track has a length of 30 meters initial when the temperature is 0 degrees Celsius. What is the length of on the hot day when the temperature is 40 degrees Celsius? So in here I have change of the length, and it is equal to alpha, coefficient of linear expansion, initial length, and the change of the temperature. Remember that if I have the change of the temperature, I don't necessarily have to convert it into kelvins. All I have to subtract them. So I have the change of the length is equal to linear expansion is 1110 to the negative 6, 1 over Celsius measurement, times the initial length, which is 30 meters, and the change of the temperature, and the temperature change from 0 to 40 degrees. Now, if I calculate the change of the length, I'm going to get 0.0132 meters. So the new length, the final length after the expansion, is going to be 30.0132 meters. And the expansion is actually, or by how much it changed, by 1.3 centimeter. In the next question, I have a circular copper ring, and they give you the linear expansion at 20 degrees Celsius has a hole with an area of 9.98 centimeters squared, so that's 9.98 10 to the negative 4 meters squared, because if you square centi, that gives you -4, because centi stands for -2, and then you square. What minimum temperature must it have so that it can be slipped onto a steel, and the linear expansion of the steel is given? A metal rod having a cross-sectional area of 10 centimeters squared. So let's look at this question and everything that is given that we can use to solve. So here what is given, and I can do the change of the to use change of the area for copper formula. So I have the change of the area for copper is equal to, they only give me linear expansion coefficient, so I have to do twice the linear expansion coefficient, and then times the initial area of the copper, and then the change of the temperature. So I am looking for the change of the temperature. If I plug in my numbers, so here I plug in my numbers, I had to find by how much I want the area to change. So I wrote, I subtracted 2 areas and figure out, and centimeters have to be -4 because it's squared. So from here I find that I underlined for color, so you see how I plug in my numbers. So for temperature, I find that the change of the temperature has to be equal to 58.9 degrees Celsius. So they ask you at what temperature they will have the same area. So the new temperature of copper must be equal to 78.9 degrees Celsius, because the temperature change has to be 58.9, and we started at 20 degrees Celsius. Question B asks, suppose the ring and the rod are heated simultaneously. So what change in temperature of both will allow the ring to be slipped onto the end of the rod? So if I change their temperature at the same time, that means the temperature change in copper, the area in copper, has to be equal to wherever the change of the area in steel, but more, because it's already missing initially 0.02 10 to the -4 meters squared. So I need copper to change by this much more in order for it to slip on top of the rod. So now if I again plug in my numbers, and the change of the temperature is going to be the same for both of them, and again I have to multiply my linear expansion that they give you by 2 because I need the area expansion. So I get delta T for the second part of this problem is equal to 167.62 degrees Celsius. So both of them have to be, so we started with 20 degrees, so both of them have to be at the temperature of 187.62 degrees Celsius. So their temperature must rise by 167.62 before the copper ring can be put on top of the steel rod. In this question, they ask you to estimate the fractional change in the volume of Earth's ocean, so the change of volume over the volume right now, due to the average temperature change of 1 degree Celsius. And they give you the volume expansion for water. And then what will be the increase in depth of the ocean if the average depth of the ocean is right now 4 kilometers, to estimate the change in depth. So let's look at the volume change for the liquid when we have the coefficient of volume expansion. So the fraction of the volume change over the volume that we have right now is 2 10 to the -4. And then let's see by how much the water is going to rise if we use the same for linear expansion. So for linear expansion, I have delta L, it's the height of the ocean, is going to be equal to initial height of the ocean, delta T. So this is beta divided by 3 to get the linear expansion. And then I have L sub 0 delta T, and that will be equal to, and I get 30 centimeters high. And 30 centimeters high is probably going to be close to from the floor to your knees. So that's about 30 centimeters. That's by how much the water is going to rise. And that's not to mention by how much the volume already changed. So if the volume is already changed, so it's going to be more than 30 centimeters rise. But if the volume wasn't changed and you just heated up the water that you already have now without the expansion, this is by how much the height would rise. And on top of it, adding all the ice that is melting, so that's going to be much higher. And I believe in 2018 United Nations Intergovernmental Panel on Climate Change met, and they said that we only have 10 more years or 12 more years, now it's 10 more years, before we reach the critical threshold of 1.5 degrees Celsius increase. That's about 2.7 degrees Fahrenheit. The increase compared to the pre-industrial levels, and that means that the global net emissions of carbon dioxide would need to fall by 45% compared to 2010 to 2030 and reach a net zero around 2050 in order to keep the warming around 1.5 degrees Celsius. They also said that even if the warming is kept below 1.5 degrees Celsius, if we start it now, the impact will be still widespread and significant. And part of that impact is not only the melting and the rising of the waters around the planet, but also the melting ice that is releasing the viruses that we living organisms did not see for millions of years. So now we may encounter those viruses and have to deal with them. Not to say about the harsher summers and hotter and droughts and hurricanes and many other disasters that may cause this increase of temperature. In this question, they say 1 liter, and again, 1 liter is the same as 1 × 10⁻³ meter cubic aluminum. And they give you linear expansion of the aluminum cylinder at 5 degrees Celsius is filled to the brim with gasoline at the same temperature. And they give you the volume expansion for the gasoline. If the aluminum and gasoline are warmed to 65 degrees Celsius, so their temperature increases by 60, both of them, how much of the gasoline will spill out? So here I use the volume expansion for aluminum first, and I need to 3 times the linear expansion of the aluminum to get the volume expansion of it, and I will do the same for the volume of the gas change or gasoline. So I did the volume for the gasoline change, I did the volume for aluminum change, and then I calculated by how much gas is going to be spilled. I subtracted one from another, and I got 53.48 10⁻⁶ meter cubic, or it's the same as 53.48 centimeter cubic, because centi cubed is going to give me -6. I will stop our video on heat number 1 at this point. I didn't get the chance to cover ideal gas in this video, so it's coming in heat 2 video. I also have not seen any of the expansion formulas given on AP formula sheets. So if you have a problem related to this, it's probably going to be either conceptual or they will give you the formulas within the problem that they give you where you have to use it. And so this will conclude our video 1 on heat, and thank you for watching. I'll see you in the next video.